One of these steam locomotives weighed over 1 million pounds. Another produced more horsepower than a modern diesel. And yes, one was longer than a Boeing 747. This is not a list of trains. It's a list of monsters. Today, we travel through steam and steel, where engineering ambition met mechanical artistry as we explore the 13 most colossal steam locomotives ever built. Titans that conquered mountains, hauled impossible loads, and pushed the boundaries of what was mechanically possible. These iron giants represent the pinnacle of steam technology, each one a testament to human ingenuity and the relentless pursuit of power. Number 13. At 140 tons, the British Railways Class 9F locomotives marked the final chapter of steam power in Britain during the 1950s. These engines were designed with one singular purpose: to haul the heaviest freight trains with unprecedented efficiency. The 210-0 wheel configuration provided maximum adhesion for pulling power, with all 10 driving wheels working in unison to move massive loads across Britain's challenging terrain. Built during the twilight of the steam era, the Class 9F incorporated decades of locomotive engineering wisdom. Their high-capacity boilers operated at 250 pounds per square inch, generating tremendous steam pressure that translated into raw pulling power. The mechanical stoker system automatically fed coal into the firebox, maintaining consistent heat even during the most demanding climbs. These locomotives were engineered to operate efficiently across Britain's diverse geography, from the rolling hills of the countryside to the steep gradients of industrial regions. Their advanced steam circulation system optimized fuel consumption, making them remarkably economical, despite their massive size. The Class 9F could maintain steady speeds with loads that would have challenged earlier locomotives, proving that British engineering could still innovate even as diesel technology loomed on the horizon. The demise of the Class 9F came swiftly with the British Railways Modernization Plan. Despite their advanced design and proven reliability, these magnificent machines were retired after barely a decade of service, victims of the diesel revolution that swept across Britain in the 1960s. Number 12. The Russian P-36 locomotives, known as the General, represented the zenith of Soviet steam engineering in the 1950s. At 170 tons and nearly 100 feet long, these elegant machines embodied both power and grace. Their distinctive Red Star emblem marked them as symbols of post-war Soviet industrial might, designed to conquer the vast expanses of the Russian landscape. The 484 wheel arrangement provided the perfect balance of power and speed for passenger service across the Soviet Union's transcontinental routes. These locomotives were built to handle the extreme conditions of Russian winters, with specialized heating systems and robust construction that could withstand temperatures that would cripple lesser machines. Their high-pressure boilers and advanced steam circulation system delivered exceptional performance while maintaining fuel efficiency across thousand-mile journeys. The P-36 class featured innovative engineering solutions tailored to Russian conditions. The firebox was designed to burn lower-grade coal efficiently, while the tender carried massive quantities of fuel and water for extended runs between stations. The locomotive's streamlined design wasn't just for show. It reduced wind resistance during high-speed runs across the steppes, helping achieve sustained speeds of 80 miles per hour. These locomotives operated the Soviet Union's premier passenger services, connecting Moscow to distant cities across the empire. Their reliability and comfort made them the preferred choice for long-distance travel, earning them legendary status among Soviet railway workers. The P-36 class represented the last great steam locomotives of Russia, marking a graceful transition from steam to diesel power in the late 1950s. Number 11. The German DR Class 45 locomotives of the late 1930s were engineering marvels designed to handle the Reich's heaviest freight demands. At 200 tons and 85 feet long, these locomotives featured the 210-2 wheel arrangement that provided maximum tractive effort for moving enormous loads across Germany's industrial heartland. Built during a period of rapid industrial expansion, the Class 45 incorporated advanced German engineering principles. Their high-pressure boilers operated at exceptional efficiency, while mechanical stokers ensured consistent firing even during the most demanding operations. The feedwater heater system pre-warmed the water entering the boiler, increasing thermal efficiency and reducing coal consumption. Innovations that would influence locomotive design worldwide. These locomotives were specifically designed for Germany's varied terrain, from the flat northern plains to the mountainous regions of the south. Their powerful cylinders and precisely engineered valve gear delivered maximum power at low speeds, making them ideal for starting heavy freight trains on steep gradients. The Class 45 could maintain steady progress with loads that would stall lesser locomotives, proving German engineering excellence. The robust construction of the Class 45 enabled them to operate reliably in demanding conditions. Their all-weather cabs protected crews during harsh winters, while the locomotive's mechanical systems were designed for easy maintenance in railway workshops. These features made them workhorses of the German freight network throughout the 1940s. The end came with Germany's post-war reconstruction and the gradual shift to diesel power. Many Class 45 locomotives were destroyed during the war, while survivors were eventually scrapped as diesel technology made steam power economically obsolete by the 1960s. Number 10. The Southern Pacific GS4 locomotives of the 1940s combined raw power with striking elegance. At 475 tons and stretching over 110 feet, these 484 locomotives were designed to be the ultimate passenger haulers, capable of maintaining 100-mile-per-hour speeds with heavy streamlined trains across California's challenging terrain. The GS4's 4,800 horsepower engine was a masterpiece of precision engineering. The locomotive's streamlined design wasn't merely aesthetic. Every curve and line was calculated to reduce wind resistance and improve efficiency at high speeds. The orange and red daylight livery made these locomotives instantly recognizable. But beneath that striking exterior lay some of the most advanced steam technology ever developed. These locomotives were built to conquer the demanding geography of the American West. The steep grades of the Sierra Nevada and the long stretches of desert terrain required locomotives that could maintain high speeds while carrying substantial loads. The GS4's large driving wheels and precisely balanced reciprocating machinery enabled smooth operation at speeds that would have caused destructive vibrations in earlier designs. The GS4's firebox was engineered to burn oil rather than coal, taking advantage of California's abundant petroleum resources. This fuel choice eliminated the need for coal storage facilities and reduced maintenance while providing consistent heat output. The locomotive's advanced steam circulation system maximized efficiency, enabling sustained high-speed operation across 1,000-mile routes. The decline of passenger rail service in the 1950s spelled doom for the GS4 class. As airlines captured long-distance travelers, these magnificent locomotives found themselves without a mission. Most were scrapped, though a few survivors remain as testament to the golden age of American passenger rail. Number 9. The Chesapeake and Ohio Allegheny locomotives of the 1940s were built for one purpose: to conquer the steepest, most challenging mountain grades in America. At 1.1 million pounds and 125 feet long, these giants possessed an astounding 7,500 horsepower, making them among the most powerful steam locomotives ever constructed. The 2666 wheel configuration was revolutionary, providing maximum adhesion for climbing the brutal grades of the Allegheny Mountains. These locomotives were engineered to haul 5,000-ton coal trains up gradients that would defeat lesser machines. The articulated design allowed the massive locomotive to navigate curves that would be impossible for a rigid frame engine of similar size. The Allegheny's high-pressure boiler system operated at the cutting edge of steam technology. The firebox was enormous, capable of burning massive quantities of coal to maintain steam pressure during sustained climbs. The locomotive's mechanical stoker could feed coal at rates that would exhaust human firemen, while the advanced steam circulation system ensured maximum thermal efficiency. These locomotives were specifically designed for the geography of West Virginia's coal country. The steep gradients, tight curves, and heavy loads demanded a locomotive that could maintain consistent pulling power regardless of conditions. The Allegheny's sophisticated valve gear and cylinder design delivered maximum tractive effort at low speeds, essential for starting heavy trains on mountain grades. The Allegheny class represented the pinnacle of articulated steam locomotive design. Their smooth ride quality, despite their massive size, was achieved through careful engineering of the locomotive's suspension and weight distribution. This attention to detail made them surprisingly comfortable for crew members during long mountain crossings. The end came with the dieselization of American railroads in the 1950s. While the Allegheny locomotives were supremely capable, diesel-electric locomotives offered lower operating costs and reduced maintenance requirements. These magnificent machines were retired after barely a decade of service, victims of technological progress. Number 8. The Pennsylvania Railroad's Q2 locomotive of the 1940s pushed steam technology to its absolute limits. At 1.2 million pounds and 120 feet long, this locomotive generated an incredible 8,000 horsepower, making it one of the most powerful steam engines ever built. The unique 4464 wheel arrangement represented Pennsylvania Railroad's innovative approach to locomotive design. The Q2's duplex drive system was revolutionary, using 2 sets of cylinders and driving wheels to distribute power more evenly. This design eliminated the massive reciprocating forces that plagued conventional steam locomotives, allowing for smoother operation at high speeds. The locomotive's high-pressure steam system operated at the bleeding edge of what was mechanically possible in the 1940s. Built for the demanding terrain of the Pennsylvania Railroad's main line, the Q2 was designed to haul heavy freight trains at unprecedented speeds. The locomotive's advanced valve gear and cylinder design delivered maximum power across a wide range of operating conditions. The duplex drive system reduced wheel slip, a constant problem with conventional high-powered locomotives. The Q2's firebox was a marvel of thermal engineering, designed to burn coal with maximum efficiency. The locomotive's mechanical stoker and advanced combustion system could maintain consistent steam pressure even during the most demanding operations. The tender carried enormous quantities of coal and water, enabling extended runs between servicing stops. Despite its impressive specifications, the Q2 suffered from mechanical complexity that made it difficult to maintain. The duplex drive system, while theoretically superior, required precise adjustment and frequent maintenance. Additionally, the locomotive's high power output often exceeded the capabilities of the railroad's infrastructure, causing track and equipment damage. The Q2's service life was brief, lasting only until the early 1950s, when diesel locomotives proved more reliable and economical. The complexity that made the Q2 so powerful also made it impractical for everyday railroad operations, leading to its early retirement. Number 7. The Union Pacific Big Boy stands as perhaps the most famous steam locomotive ever built. At 132 feet long and 1.2 million pounds, these giants were engineered to conquer the Rocky Mountains with 4,000-ton freight trains. The 4884 wheel arrangement provided the perfect combination of power and stability for mountain railroading. Built in the 1940s, the Big Boy represented the culmination of American steam locomotive engineering. 25 of these magnificent machines were constructed, each one a testament to the marriage of power and precision. The locomotive's 6,290 horsepower could move impossibly heavy loads, up grades that would defeat lesser machines, while maintaining speeds up to 80 miles per hour on level track. The Big Boy's design was specifically tailored to Union Pacific's overland route between Wyoming and Utah. The steep gradients and long distances required a locomotive that could maintain consistent power output for hours. The enormous firebox could burn 22 tons of coal per trip, while the mechanical stoker ensured consistent firing regardless of conditions. The articulated design allowed these massive locomotives to navigate curves that would be impossible for a rigid frame engine of similar size. The front engine truck could pivot independently, enabling the Big Boy to follow track curvature while maintaining all wheels in contact with the rails. This flexibility was essential for operation on mountain railroads with their tight curves and steep grades. Despite their massive size, the big boys were renowned for their smooth ride quality. The locomotive's advanced suspension system and precise weight distribution eliminated the harsh riding characteristics common in earlier articulated locomotives. This smoothness was achieved through careful engineering of every component, from the driving wheels to the cab suspension. The big boys' decline began in the 1950s as diesel-electric locomotives proved more economical for freight operations. The last big boy was retired in 1959, ending an era of steam supremacy on American railroads. Today, one big boy remains operational, serving as a rolling museum of steam technology. Number 6. The Soviet A-20 locomotive of 1934 represented an early attempt to create the ultimate freight hauler. At 140 tons with a 2882 wheel arrangement, this articulated giant was designed to move massive loads across the vast distances of the Soviet Union. The AA-20 was an experimental locomotive that pushed the boundaries of what was possible with 1930s technology. The locomotive's compound articulated design used high-pressure steam in the rear cylinders, with the exhaust steam then used in the larger front cylinders. This system maximized the energy extracted from each pound of steam, improving efficiency on the long hauls typical of Soviet railroads. The AA-20's firebox was designed to burn low-grade coal efficiently, taking advantage of the Soviet Union's abundant coal resources. Built during the Soviet Union's rapid industrialization, the AA-20 was intended to support the massive construction projects of the first five-year plan. The locomotive's enormous pulling power made it ideal for hauling heavy construction materials and industrial equipment to remote locations. The robust construction was designed to operate reliably in the harsh conditions of the Soviet winter. The AA-20's design incorporated lessons learned from American articulated locomotives, adapted for Soviet conditions. The locomotive's boiler was designed to operate at lower pressures than contemporary American designs, sacrificing some efficiency for increased reliability. This approach reflected Soviet engineering philosophy, which prioritized durability over maximum performance. The experimental nature of the AA-20 meant that only a few were built. The locomotive's complexity and high maintenance requirements made it impractical for widespread use. Additionally, the rapid development of diesel technology in the post-war period made further development of steam power unnecessary. The AA-20 remains a fascinating example of Soviet engineering ambition during the steam era's final decades. Number 5. The Duluth, Misabe, and Iron Range. Yellowstone locomotives represented the ultimate in specialized steam power. Built in the 1940s, these two 884 giants were designed for one specific purpose: hauling massive iron ore trains from Minnesota's mines to Lake Superior ports. With 140,000 pounds of tractive effort, they were the most powerful locomotives of their wheel arrangement ever built. These locomotives were the most powerful Yellowstones built, producing 140,000 pounds of tractive effort, making them capable of starting trains that would stall lesser locomotives. The DM&IR's specialized cargo of iron ore was so heavy that normal freight cars couldn't carry it. The railroad used short ore jennies, specifically designed for this dense cargo. The Yellowstone's design was perfectly suited to the DM&IR's unique operating conditions. The four-wheel trailing truck was added to accommodate a larger firebox and a longer, all-weather cab for Minnesota's bitter winters. The locomotive's articulated design allowed it to navigate the tight curves common on ore branch lines, while the massive firebox could maintain steam pressure during the sustained climbs away from the mines. Operating at a boiler pressure of 240 pounds per square inch, it delivered 140,093 pounds tractive effort. The locomotive's mechanical stoker could feed coal at enormous rates, necessary to maintain steam pressure, while hauling trains that could exceed 15,000 tons. The advanced steam circulation system ensured maximum efficiency, critical for a railroad operating on narrow profit margins. The geography of Minnesota's iron mining region demanded locomotives capable of operating in extreme conditions. Winter temperatures could reach -40 degrees Fahrenheit, while summer operations involved hauling trains through swamps and over rolling hills. The Yellowstone's robust construction and weather-resistant design made it ideal for these challenging conditions. The first 8 were delivered in 1941 and performed beyond the railroad's expectations, which ordered another 10 of these engines in 1943. The Yellowstones revolutionized iron ore transportation, enabling the DM&IR to move unprecedented quantities of ore to support America's World War II industrial effort. The decline of steam power in the 1950s led to the Yellowstone's retirement. Diesel-electric locomotives, while less powerful, offered lower operating costs and reduced maintenance requirements. The last Yellowstone operated in 1960, ending an era of specialized steam power on America's ore railroads. Number 4. The Pennsylvania Railroad Class S1 stands as the most ambitious steam locomotive ever attempted. At 140 feet overall, engine and tender, the S1 was the longest reciprocating steam locomotive ever built. This magnificent machine represented the Pennsylvania Railroad's determination to prove that steam power could compete with emerging diesel technology. The S1 also had the heaviest tender, 451,840 pounds or 205 tons, highest tractive effort, 76,403 lbf, of a passenger steam engine when built, and the largest driving wheels. The unique 6-4-4-6 duplex drive arrangement was revolutionary, using 2 sets of cylinders and driving wheels to distribute power more evenly than conventional designs. The S1's streamlined design by Raymond Loewy was both functional and beautiful. The locomotive's sleek lines weren't just for aesthetics. They reduced wind resistance at high speeds, enabling sustained operation at velocities that would have been impossible with conventional designs. The locomotive was claimed to have exceeded 156 miles per hour on the Fort Wayne-Chicago run, though this speed was never officially verified. The PRR S1 stands out as the longest and heaviest, 608,170 pounds, rigid-frame reciprocating steam locomotive ever built. The locomotive's massive size was necessary to house the complex duplex drive system and generate the power needed for high-speed passenger service. The S1's boiler was a masterpiece of thermal engineering, capable of maintaining steam pressure at speeds that would exhaust conventional designs. The S1 was designed for the Pennsylvania Railroad's premier passenger routes, where sustained high-speed operation was essential. The locomotive's 84-inch driving wheels and precisely balanced reciprocating machinery enabled smooth operation at speeds exceeding 100 miles per hour. The duplex drive system reduced the harsh riding characteristics common in high-speed steam locomotives. However, the engine's long, rigid frame made it unsuitable for most tracks and limited its service life. The S1's wheelbase was so long that it could only operate on the Pennsylvania Railroad's main line between New York and Chicago. Tight curves and older infrastructure made the locomotive impractical for general service. The S1's complexity proved to be its downfall. The duplex drive system required precise maintenance and frequent adjustment, making it expensive to operate. Additionally, the locomotive's high power output often exceeded the capabilities of existing infrastructure, causing track and equipment damage. Only one S1 was ever built, and it was scrapped in 1949 after less than a decade of service. Number 3, the South African class. 25 NC locomotives emerged in the late 1950s as robust workhorses designed for the challenging conditions of African railroads. At 220 tons and 108 feet long, these non-condensing engines were originally designed as condensers but modified for efficiency in warmer climates. Their 4-8-4 wheel configuration enabled them to navigate both steep mountainous terrain and flat desert stretches with equal capability. The Class 25 NC featured the innovative Watson Standard boiler, which enhanced steam capacity for lengthy journeys across South Africa's vast distances. This advanced boiler design incorporated lessons learned from decades of steam locomotive evolution, providing maximum thermal efficiency while maintaining reliability in harsh conditions. The mechanical stoker system ensured consistent firing even during the most demanding climbs through the Drakensberg Mountains. These locomotives were engineered to operate in South Africa's unique geographical challenges. From the high altitude of the Witwatersrand to the coastal plains of Cape Town, the Class 25 NC had to perform reliably across dramatically different elevations and climatic conditions. The locomotive's robust construction and weather-resistant design made it ideal for operation in temperatures ranging from desert heat to mountain snow. The Class 25 NC's design reflected South African Railways' need for versatile, reliable motive power. The locomotive's large grate area and efficient combustion system enabled it to burn lower-grade coal effectively, taking advantage of South Africa's abundant coal resources. The advanced steam circulation system maximized efficiency, critical for a railroad operating across such vast distances. The adaptability of the Class 25 NC made it invaluable for South African railroads. These locomotives could handle heavy freight trains on mountain grades, then transition to high-speed passenger service on level sections. This versatility was essential for a railroad system that needed to move everything from mining equipment to agricultural products across the country. The end of the Class 25 NC came with South Africa's transition to diesel power in the 1970s. Despite their proven reliability and efficiency, these locomotives were gradually replaced by diesel-electric units that offered lower operating costs and reduced maintenance requirements. Today, preservationists celebrate the legacy of these remarkable machines, which represented the pinnacle of steam technology adapted to African conditions. Number 2, the New South Wales Railways Garratt 70 class, introduced in the 1950s, represented a revolutionary approach to steam locomotive design. At 260 tons and 100 feet long, these unique double-ended locomotives featured 2 engines and boilers in an articulated configuration that was perfectly suited to Australia's challenging railway conditions. The Garratt design was fundamentally different from conventional steam locomotives. Instead of a single large boiler, the locomotive featured 2 separate engine units connected by a central boiler and water tank. This arrangement distributed weight more evenly and provided exceptional flexibility for navigating Australia's tight curves and steep gradients. The 482+284 wheel arrangement allowed for exceptional maneuverability while maintaining maximum adhesion. The Garratt's articulated design was ideally suited to Australia's rugged terrain. The locomotive could navigate curves that would be impossible for a rigid frame engine of similar power, while the distributed weight reduced track stress. This was particularly important on Australia's lightly built branch lines, where conventional heavy locomotives would have caused excessive wear and potential derailments. The double-ended design provided several operational advantages. The 2 separate fireboxes could burn different grades of coal simultaneously, optimizing fuel efficiency based on local coal quality. The locomotive's water capacity was enormous, essential for operation in Australia's arid regions, where water stops were hundreds of miles apart. The central boiler arrangement provided excellent steam distribution to both engine units. The Garratt 70 class was engineered for Australia's unique operating conditions. The locomotive's weather-resistant construction could withstand the extreme temperatures of the Australian outback, from desert heat to mountain snow. The enclosed cab provided protection from dust and weather, while the locomotive's mechanical systems were designed for extended operation between maintenance stops. These locomotives played a pivotal role in Australia's resource transportation network. The Garratt's enormous pulling power made it ideal for hauling heavy mineral trains from remote mines to coastal ports. The locomotive's ability to operate efficiently across vast distances made it invaluable for a railroad system connecting Australia's scattered population centers. The decline of steam power in the 1960s led to the Garratt's retirement. Diesel-electric locomotives, while less powerful, offered lower operating costs and reduced maintenance requirements. The unique design that made the Garratt so effective also made it expensive to maintain, contributing to its early retirement despite proven reliability. Number 1. The Canadian National Super Mountain U2C series, introduced in the 1930s, stands as the heaviest steam locomotive ever built at 300 tons. These magnificent machines represented the pinnacle of steam locomotion in North America, marrying unprecedented power with advanced engineering that would influence locomotive design for decades. The Canadian National Confederation locomotive type, or the Canadian National U classes, is a type of Canadian steam locomotive with a 4/8/4 wheel arrangement used on Canadian railways. The U2C series was the ultimate evolution of this design, built to conquer Canada's vast distances and challenging terrain with unprecedented power and reliability. The U2C's massive weight was distributed across the 4/8/4 wheel arrangement, providing exceptional adhesion for starting heavy trains on steep grades. The locomotive's high-capacity boiler was a masterpiece of thermal engineering, capable of maintaining steam pressure during sustained climbs through the Canadian Rockies. The advanced steam circulation system optimized fuel and water use, essential for operation across Canada's transcontinental routes. These locomotives were specifically designed for Canada's unique geographical challenges. From the prairie provinces to the Rocky Mountains, the U2C had to perform reliably across dramatically different elevations and climatic conditions. Its robust construction was engineered to withstand Canadian winters, with specialized heating systems and weather-resistant components that could operate in temperatures below -40 degrees Fahrenheit. The U2C series featured innovations that would influence locomotive design worldwide. The locomotive's mechanical stoker could feed coal at enormous rates, necessary to maintain steam pressure while hauling trains across 1,000-mile routes. The advanced valve gear and cylinder design delivered maximum power across a wide range of operating conditions, from high-speed passenger service to heavy freight hauling. They were the backbone of the CNR locomotive fleet from the 1930s to the 1950s. The U2C's reliability and power made it the preferred choice for Canadian National's premier services, connecting cities across the vast Canadian landscape. The smooth ride quality, despite its massive size, Stadtroquensis Spizity, was achieved through careful engineering of every component. The U2C's design reflected Canadian engineering philosophy, which prioritized reliability and durability over maximum performance. The locomotive's systems were engineered for extended operation between maintenance stops, essential for a railroad operating across such vast distances. This approach made the U2C one of the most reliable steam locomotives ever built. The end of the series came with Canada's transition to diesel power in the 1950s. Despite their proven reliability and impressive performance, these magnificent locomotives were gradually replaced by diesel-electric units that offered lower operating costs. The last U2C was retired in the early 1960s, ending an era of Canadian steam supremacy. These 13 giants of steam represent humanity's greatest achievements in mechanical engineering. Each locomotive was a response to specific geographical and operational challenges, pushing the boundaries of what was possible with steam technology. From the specialized ore haulers of Minnesota to the transcontinental giants of Canada, these machines conquered every terrain and climate on Earth. The golden age of steam lasted barely a century, but in that time, engineers created machines that remain marvels of mechanical artistry. These locomotives didn't just move trains, they moved nations, connecting distant cities, hauling the materials of industry, and shrinking the world through the power of steam and steel. Today, most of these magnificent machines exist only in museums and memories, but their legacy lives on in every mile of railroad track and every engineering achievement that followed. They remind us that human ingenuity, when combined with mechanical precision, can create machines that transcend their original purpose to become symbols of an age when steam ruled the rails.